sharing. Sir, but you are mute. You are mute, sir.
Now?
Yes, sir. Now it's perfect.
Now,
Good,
can you tell
good morning, everyone.
where I was?
Yes, good morning, everyone. We'll start with the third day of the FDP. Welcome, all of you. Sir, you may please take over and start.
Should I start from the degree?
Yes, sir. Yes, sir.
Oh, gosh. Right. So now, okay, what I spoke even I don't know, but I will be now being a little bit quickly repeating the things. So there were many participants who were there actually at that time.
Sir, actually, I also joined, but somebody removed me, and then after that, somebody was telling that the meeting ended also.
I see.
So these are technical things which can't be handled, and this was such a panic situation. I'm so sorry, sir. I'm so sorry.
Right. Okay. So you are repeat the telecast of what I did now. I don't know. It's going to be the same. So now today we are going to start with the concept of covariant correlation and rank correlation. And if you try to see, yesterday we had seen the graphical display of two variables, and we wanted to see whether the two variables are correlated or not. That means there exists a relationship between the two variables or not. So when we are trying to understand the degree of association between the two variables, we have to keep in mind a couple of things. Number one, when we are trying to find out the degree of association can be linear, or that this can be non-linear. For example, if you see a plot like with these points like this one, so you can see that points here are more or less linear. But if you try to see here a scatter diagram which is here like this one, so you can see here that the relationship between x and y is not really linear, but it is non-linear. So so first we have to decide for this thing. Second thing, we have to decide whether my variables are continuous or discrete. So when we are talking of the can you hear my slides?
Yes, sir.
Achha, because okay. So okay, and then so now when we are talking of the association between the two variables, there is an association between the two continuous variable. Continuous variable means, for example, if I say the number of hours of study, they affect the marks of the student. Uh, and when the weather temperature increases, we use air conditioner, fans, etc. So the electricity consumption increases as the weather temperature increases. The weights of small children, that increases with height or with age. So these two variables are interrelated. So in these cases, the variables are continuous in nature, and when the variables are continuous in nature, then we have the concept of correlation coefficient, which is actually the Carl-Pearson correlation coefficient that can be used. And second thing, what you have to keep in mind that the nature of the variables can be discrete, can be continuous, can be categorical, etc. So we are going to study here the first the degree, means how to measure the degree of association when the two variables are continuous, and the degree and the relationship between the two variables is approximately linear. For non-linear, we have another concept of correlation ratio, but that is not so popular, so I'm not doing it here. And when we have the variables like discrete or say counting variables, for example, if I say there is a group of patients which I divide into genders, say male, female, and we try to give them medicine, and after that we try to see the effect of the medicine, whether the medicine was effective or not. So in this case, what we can do, we can have a data here like this one. male and female, effective and not effective, and then we try to count that how many males found the medicine to be effective, how many females found the medicine to be non-effective, and so on. So this is your actually here with discrete or say counting variable. So in this case, the measures for the degree of association, they are going to be entirely different than the degree of than the measures what you are going to use for the continuous variable, right? And similarly, we have sometime ranked observation. For example, we have seen many times that when we conduct the viva of our students in our class, then suppose there are two teachers who are trying to give the marks to the student out of 10. So a student comes, both the examiner asks the questions, and if the student is good, then it is expected that both the examiners will give them good marks, some higher marks, and if the student is good, bad, then both the examiners will give, say, this lower marks. But definitely, when I say the higher marks and lower marks, that is the choice of the examiner, in the sense that if some student is very good, somebody may give 10 out of 10, and somebody may give 10 out of 9, and somebody may also give 10 out of 8 out of 10. So now, but but if somebody gives the marks, say this 2 out of 10 and 9 out of 10, then there is a contradiction that whether the student is good or bad, that is very difficult to understand. So what we want to do here in the case of this thing, that we would try to find out here that whether the examiners have done a fair job or not. So what we will do, that we will try to collect the marks, we will rank them. And then I will try to find out the correlation between their ranks. So that will give us an idea that how consistent were the two examiners. If both the examiners are giving higher marks to good students and lower marks to bad students, then the correlation will be higher. So in this case, we are going to use the rank correlation coefficient, right? So now let us first try to understand the correlation coefficient. A couple of very important things about the correlation coefficient that you have to keep in mind. Number one, when we are talking of the correlation coefficient, then the correlation coefficient is used only to measure the degree of linear relationship between the two variables. When there is a non-linear relationship, do whatever you want, but please don't use the concept of correlation coefficient. What do I mean? Suppose if you get the data on some x and y variable, some paired observation, and if you just use the plot command to make this type of plot, or if you get here a plot like this one, where you can see that the data is really non-linear, it is not following a linear trend. So in this case, I would say that okay, there is a linear trend like this one, but in this case, the trend is here like this one. So you cannot use the concept of correlation coefficient in this case, right? And this correlation coefficient is a statistical tool to measure only the degree of linear relationship. That is what you have to keep in mind. Believe me, many times people are using it in a very wrong way. So I believe now that here that we have got here two variables x and y, and suppose both are linearly related. So I can express their relationship by the equation like y equal to mx plus c, which is here like I said, y equal to a plus bx, where a and b are some constant, for example, intercept term and the slope parameter. Now, when we are trying to see two things, I can give you here the by this picture, and then I will come to the definition. When you are trying to increase here this value of here x, and then the value of y are increasing like this way, you can see. So there is a sort of increasing trend. Here, when you are trying to increase the value of x, then the values of y's are decreasing. So there is a here, and so there is here a decreasing trend, right? So in this case, we say the sign of the relationship is positive, And here if we say that the sign of the relationship is negative, because as x is increasing, y is decreasing, right? And in this case, you can see here when you are trying to increase x, there is no clear relationship between the y, whether y is being affected by x or not. So we say that here there is no correlation. So based on this, we are trying to use the concept of correlation coefficient. There are two things what we have to keep in mind. One is the sign, which is indicating the direction of the relationship, and second is the magnitude. What do you mean by magnitude? I will try to explain you. And so now I can say that if x is increasing, or if one variable is increasing and another variable is also increasing, then the relationship is said to be positive, right? So if both the variables deviate in the same direction, if x increases, y also increases, and vice versa, then this is called as a positive correlations, or the variables are called as positively correlated. And similarly, the opposite is when x increases, then y also, then y decreases. So there is a opposite type of relationship between x and y. So we say that the x and y are negatively correlated, and this correlation is negative, right? And if one variable changes and the other variable remain constant on an average, then that means there is no change. When you try to change x, there is no effect on y, or vice versa, then we say that there is no correlation, right? So you can see here that in this case, if I try to see here, that if I try to fit here a line like this one, here also I can fit here a line like this one, sorry, but like this one rather. So if you try to see here the points are more spreaded around the line, whereas here the points are more closer to the line. Right. So in this case, we say that okay, the degree of linear relationship is stronger and it is positive than the figure number here too. One thing I would like to emphasize here, that when you are trying to look into the degree of relationship between the two variables, I have used here two terminologies. One is here zero correlation, and another here is independent variables. Right, here you have to be very careful. Means if I say here, if the two variables are independent means statistically independent. We have some definitions of independent, that how you can check mathematically, but anyway, I'm not going into that direction. But the concept is the same, that the occurrence of one variable does not affect the occurrence of another variable. In that case, if the two variables are independent, they will imply that the correlation between the two variables is zero. Right, there is no linear relationship between the two. But on the other hand, if the correlation is equal to zero, then this does not imply that the two variables are independent. Why? Because those variables may have a relationship like this one, non-linear relationship. So since the correlation coefficient is trying to measure the degree of linear relationship, so in this case, the degree of linear relationship is zero, so correlation coefficient will be zero, but it doesn't mean that the two variables are independent. They have got some non-linear relationship, right? Right, so now the question comes here, okay, graphically I can view all these things, but definitely I would like to take some concepts on the I will try to take some conclusions based on some so-called mathematical functions in a numerical way. So in order to understand those things, we have a concept of covariance and correlation. Can you recall the concept of variance? Variance we had defined as summation xi minus x bar whole square, right? So I can write down here summation xi minus x bar into xi minus x bar, and it was trying to measure the degree of concentration around the central value, like is here, right? So now how to define the concept of covariance? The covariance will happen only when there are two variables. That means one variable is trying to affect the other variable. So exactly on the same way, the way we have defined here the variance, what I can do here, that instead of using here now one variable, I have here two variable x and y. So I can do here one thing, one of this xi minus x bar I can replace by say yi minus y bar. So don't you think that this is going to work just like a variance, and it will give us an idea about the covariance? Right. So you can see here, this is how we are trying to define the value of covariance based on the paired observation x1, y1, x2, yn, xn, yn. So x2, x1, y1 means, okay, you try to find out the height and weight of the child number 1, then height and weight of the child number 2, height and weight of the child number 3, and so on. So you can see here that statistically defined, it is defined here as with the divisor here 1 upon n, but when you are trying to compute it in the R software, we have a command here COV, and inside the parentheses you have to write the variable x comma y if x and y are the two data vectors. But here also we have the same thing that happened in the case of variance, that when R is trying to compute it, here the divisor here is 1 upon n minus 1. Right. So, and the reason for this n minus 1 is the same here, that because when we try to estimate the unknown covariance of the population on the basis of given sample of data, then there are two different methods to estimate it, and those two methods give us two different values, one with divisor n and say another with divisor n minus 1. Right. So, but anyway, if your sample is large, then it does not make any difference. Otherwise, you can also use this covariance function, and you can just adjust it by multiplying by n and dividing by n minus 1 to get the covariance with the divisor n. But practically that doesn't make any difference, and particularly when you are trying to look into this data science, the data is going to be huge. So 1 upon n or 1 upon n minus 1 will not make much difference. Okay. So now the question here is this, this covariance is lying between minus infinity and plus infinity. So we want to have a measure which is lying between the finite limits so that I can understand the degree of linear relationship. And when we are trying to understand the degree of linear relationship between the two variables, don't you think that that beside the covariance, we should also take care of their individual variances? Right. So we are looking into this aspect and considering this aspect as a measure of degree of linear relationship is defined here like this. Simply try to take the covariance between x and y divided by standard deviation of x and standard deviation of y, or it is the square root of variance of x and variance of y. If you try to just write down it here basic, this will come here like this. And you see, means this if you try to expand this summation xi minus x bar whole square, then this can be very easily written as summation xi square minus n times x bar square. So either you use this term or this term, that doesn't make any difference. And one of the popular symbol to indicate this correlation coefficient is R. Right. So this is the mathematical formula of this correlation coefficient. But anyway, you are not going to compute it manually. The software will get a job, but it is important to understand how it is going to be interpreted. The limits of this correlation coefficients are between -1 and +1. Right. So the lowest value can be -1 and the highest value can be +1. So now if the value of R comes out to be greater than 0, that indicates the positive association between x and y, and we say that x and y are positively correlated. And if R comes out to be negative, then we say that the two variables are negatively correlated. They are and there is a negative association between the two variables x and y. And similarly, if R is equal to 0, that is indicate that there is no association between x and y, and we say that x and y are uncorrelated. But usually people say that okay, they are independent. Okay, in some rough sense you can talk about this statement, but statistically it is a better option to call it as x and y are uncorrelated. For the independence, we have different types of things, but in a common sense, people do use it in the same sense. Okay, so you have to just keep in mind. So you can see here when you are talking about this correlation coefficient, it has two things. One is here the magnitude, and here and another here is the sign. So in case of the sign of the correlation coefficient is positive, that will increase, that will indicate the positive correlation, and the negative sign will indicate the negative correlation, as simple as that. And what is the meaning of positive and negative correlation? That I already have explained you, that if one variable increases, another also increases, or if one variable increases, other variable decreases, right? So there should not be any problem. And ideally, if you try to see, if you try to take here r equal to 1, this is the perfect linear relationship. Means all the points, they are exactly going to lie on this straight line, no deviation at all. And if r is equal to 0, that means there is no correlation. So and then any value of r between 0 and 1 will give you suitable idea about the degree of linear relationship. And when we try to take the two extreme values are equal to +1 and -1, this is called a perfect linear increasing relationship and perfect linear decreasing relationship between x and y respectively. Right, so the interpretation is very simple. So if I try to show it here graphically, well, I have made this things on the paint myself, so the picture may not be 100% accurate, but it will give you a fair idea. If you try to see here, we have a curve here like this, where if you try to plot a hypothetical line, it will look like this, because this is linear trend. So if you try to see here, in both the cases we have a decreasing trend, so this degree of correlation coefficient is going to be minus. The sign of the correlation coefficient is going to be minus. And if you try to see here the points are more closely clustered around the line in comparison to this line. So means this can be indicated by the value of correlation coefficient to be 0.9 and here to be 0.5. And similarly, when they are independent, that will be 0 ideally. And then if you have a increasing relationship, once again you can see here, if there's a similar structure that these points are lying somewhere here, and in comparison to this picture, the points are lying here, but in this picture the points are more close to the line as compared to this first picture. And if all the points are exactly lying on the straight line, then it is the correlation coefficient 1. So this is how we try to do that when we try to, whenever the data comes to us, we try to look into the scatter diagram, or we simply use the plot command to get such an idea, right? And then means these things, if you try to look into the data science, you are really not interested in most of the cases in a single variable, but you want to see the fact that what should you do that is going to affect the outcome. For example, if I'm talking about this online shopping websites, right? If you try to see, sometime they will give you some offers, sometimes they will give you some surveys to understand what do you want. Recently, a couple of days back, I got a link from the Amazon.com where they were asking me, okay, what type of promotion do you prefer when you try to buy the grocery item? One is this: immediately if you buy for say more than 2,000 rupees, then okay, then 10% is straightforward off. Second thing is this: okay, if you buy for 2,000 rupees, then 10% will be the cashback that will be credited after 90 days. And then okay, instead of 10% cashback, you can avail some points that can be encashed for different types of things. So this way they are trying to understand what people want. They are simply trying to see the relationship between the variables, the choice of the customer and the action which will trigger the sale. Right. Similarly, you can see here that if somebody is going to the website for purchase, say, around different time periods of the year. For example, you can see that more number of people are trying to access this shopping website during the festival time, like as Eid or say Holi or Diwali or Bakri or something else, like Christmas, New Year's, etc., etc. Right. So at that time, they know that okay, people want, so they will try to give different types of offer, different types of promotion. So these things helps them in finding out such a relationship. Okay, so now the question comes here, how are you going to compute it in the R software? So covariance I already have told you, and if you want to compute here the correlation coefficient, then the simple command here is COR. COR means XY. And if you try to see here, there are many options if you go to the help. So I will try to use here only two options. One is here about the variables. Use everything means you have to use the entire data set. So you don't even need to use it. But the more important part here will be the method. As I said that this Carl Pearson correlation coefficient is the correlation coefficient which we have defined. This is your actually Carl Pearson correlation coefficient, and this is being computed by default also. If you don't give any method here, then it will be simply the correlation coefficient. And similarly, we have another measure, Kendall measure. I'm not going to discuss it here, but when we want to compute the rank correlation coefficient, then this rank correlation coefficient was given by Spearman. So this is called actually as a Spearman rank correlation coefficient. So in that case, you have, if you try to give the method equal to Spearman, then the same formula will compute the same command will compute the rank correlation coefficient. So you can see it is not difficult here, right? So and here I have given here the details of that how you can use here, right? So anyway. So if you try to means I just want to show you here a couple of things. For example, if you try to take here two data sets, C1234, C1234, and if you try to find out their covariance, that will come out to be 1.66 like this. And if you try to take one variable positive and say another variable all negative, you can see here the magnitude is the same like this one, but the sign here is now changed. Right, so that is the idea that when you are trying to look into this in the structure of this correlation coefficient here, you can see here that this variance is always going to be positive. This part is always positive. So this is the part covariance which is trying to indicate whether the relationship is positive or negative. So that is what I have shown you here, that if you try to take all the positive observation, this is going to be positive, and if you try to take one positive and one negative, then this is going to be negative, right? Okay. And now, in case if you try to find out the correlation coefficient between the two variables, if you try to take one observation as say 1, 2, 3, 4, and this observation here as say 1, 2, 3, 4, so you can see here that means if you try to plot it, this will look like 1, 1, 2, 2, 3, 3, 4, 4, and they are exactly lying on the 45-degree line, exactly on the line. And in this case, the correlation comes out to be here 1. Right, so means you can just write them on the R console. It is means I'm giving you here the screenshot, and it is not difficult at all. And similarly, if you try to take here one variable here as say 1, 2, 3, 4, another here as say -1, -2, -3, -4, mean one positive, one negative, then you can see here the correlation coefficient is coming out to be -1. And if you try to plot them, there is a decreasing relationship like this one. And this is here the value with the minus sign. So I mean, I have taken here two extreme examples to convince you that when you are trying to take this type of variable, one is increasing, one is decreasing, then the sign is negative, otherwise that is positive. Right. So similarly, if I now try to take an example to show you that how the things are going to work. So this is the same example that I took yesterday. There are 20 students, they have been awarded the marks out of 500, and the data has been collected that how many number of hours per week they have studied. So it is like here is student has studied 23 hours and he or she has got 337 marks and so on. So now I try to store these two data set in these two data vectors, marks and hours. And yeah, and then you can here plot them. You can see here when you try to plot them, well, it is a nearly straight line. Well, 100% exact line, it is difficult to get, but there is going to be some variation. But you can see that, okay, the relationship can be approximated linearly in a decent way. It's not bad, right? So, and if you try to make here a scatter smooth diagram, that is also indicating that what type of line you can fit. But the better option here is to fit a linear regression model that we will be doing possibly tomorrow by uh, by another eminent speaker. So yeah, so that will give you a straight line here like this thing, and it is not different. There is a command here actually AB line that you can use, and then this line can be obtained. But I'm not discussing it here, because otherwise you will ask me what is the basic philosophy behind this line, how you have computed it. So I'm not doing it here, but it's not difficult. So in this case, if you try to see here, if you try to find out here the marks, the correlation coefficient between marks and hour, this is coming out to be 0.996. And right, and then if you try to see here, means if you try to interchange marks and hours, then again this is the same thing, and it is obvious that the correlation coefficient is a symmetric measure, in the sense that it is that whether you try to find out uh, uh, that the correlation coefficient between x and y and x, they are going to be the same thing. And you can see here that the sign of the correlation coefficient is positive. So that is obvious. We always tell to our student that, okay, if you try to study more, your marks are going to be increased. That is the simple interpretation of this concept. Right. This is here the screenshot. Okay, I think if you have any questions, first you can ask, and then I will come to the rank correlation. The meantime, is I will try to show it on the R console also. So if you have any question, please feel free. Right, so let me try to first copy this data here, and then I have entered the data here, and if you try to see here, if I try to plot marks and hours, you can see here this type of graphic, and if you want to find out here the variance, the covariance between these two variables, so I can say here COV, but definitely it is giving you a positive value, but it is not indicating anything out of this thing. So instead of this, if you try to find out here the correlation, it is 96 that you can see. And similarly, if you try to take here two variables here, x is equal to here, say here C, or say 1 to here 4, and y here as also here 1 to here, right? So, and if you try to plot it here, plot x, y, that this is here, you are getting the same line. And if you, means I can take here more number of points, for example, I can take here 400 and y is equal to here, and then I try to plot here, plot x and y. See here, this is the complete straight line. And if I try to say here y is equal to minus y, right, then if I try to plot here x and y, you can see here that this is perfect linear relationship, right? And if I try to find out the correlation coefficient between this x and y, you can see here this will come out to be -1. Wait, I can show you here. Wait, -1. So that confirms that the way you are trying to take the decision, that is confirming that what you are doing that is correct. Because one thing you always have to keep in mind actually, means essentially working in data science is something like working with the God. Right, you will laugh at me, but please pardon me. I'm not trying to hurt anybody's feeling, but it is something like, at least if you ask me when I go to the temple, I will always ask something to God. Okay, God, please do this thing. Please do this thing for me, like this thing. And I cannot see the God, but I believe that there is a God. And I try to do something so that I can please the God and I can get whatever I want. And if I want to get a good marks in my examination, I will say, God, please give me good marks. But if I want to have some good food, then I will say, God, please give me some good food. So the way I'm trying to demand with the God, I expect that God is going to fulfill my wish. So that is the same thing is happening with the data science also. That data science means the data is too huge and we just cannot see from our eyes. But if you ask in the correct way to the data, you prepare your questions in the proper way and you use the proper tool. For proper tool means sometimes people say that, okay, if you take this besan ka laddu for the Hanumanji, then he will become pleased. And if you take this thing to that God, he will be pleased. Well, I say that, okay, God is giving us or we are going to give the God, right? It is only the human being that can be pleased with this with the food. God cannot be pleased possibly. I don't know, right? But anyway, if you means offer your prayers with a proper tool, with a proper gift, you feel more confident that God is going to fulfill your wish. Exactly, is the same thing here is with the data also. If you try to use the correct tool on the correct data, then you will get the good outcome. And we have got different gods for different jobs, right? So that is the same thing with the data science also. So now I come to another concept here, that is the rank correlation coefficient. Rank correlation coefficient means, as I said in the beginning, that you have here two types of hello.
Yes, Dr. Rashmita has some questions.
Yes, kindly ask.
Dr. Rashmita, you are on mute, Dr. Rashmita. Please speak.
One thing you have
No,
to
madam,
keep
I
in
told you
mind,
to
this I
mute
can share
me.
my screen. I
Sorry.
cannot see anyone. I cannot see who is there on the screen. I can see only my slides. So unless and until you speak, Miss, I will not even be come to know that somebody is asking any question. Yeah, kindly ask.
I can see JN Tripathi, sir. Just making you the presenter, sir. You can ask. JN Tripathi, sir.
Sir, you have shown correlation between hours and marks, and then correlation between marks and hours.
Yes.
I mean, x and y variables have been interchanged.
Yes.
The result is same. Is it the
Yes.
case for every case? I mean, in every condition, this condition must satisfy.
Actually, if you try to see, your mathematical expression is like this.
Yeah,
So
now I understand. Now I understand, sir. Okay,
right.
there
So
is
so
no
summation xi minus x bar into
there is
yi.
no change. That is not going to occur.
Right. It's something like summation xi yi is the same as summation yi xi.
Yes, sir.
So
Thank you.
that is
Thank
why
you.
this is happening here. Yeah, and yeah, I mean, Dr. Tripathi has raised a very valid question in the sense, you see, that is what is our job from the statistics point of view. We have BSc statistics, MSc statistics, PhD statistics. So people do try to develop these tools from the mathematical point of view, which can give us the correct value. Right, and these properties, what they are, what Dr. Tripathi has asked, yes, they are not coming from his type, but they are true. They are based on the mathematical proof. And many times when the things become more complicated, as I said in the beginning in my inaugural lecture, then we go for the computation, and based on the computation, we try to observe such a phenomena. So that is why we have the branch, we have the subject is called as mathematical statistics.
Oh, another question, sir.
Yes.
We can have two types of plots. One is plot, another is scatter smooth plot. So the data points in the scatter smooth plot, only a straight line is added, or the data points are also shifted, or
No,
some.
no. The data points will remain the same in the smooth scatter plot. It will only create a smooth plot that may not always be exactly a straight line. That can be a little bit non-linear line, but it is trying to show you the pattern of the data. Now the question will come here that if you are getting here a line like this one, right? That I can this I can means approximate by here like this line. So that is the job of the linear regression analysis, that an approximately linear relationship is provided by the tools of regression analysis. So a scatter smooth plot will give you only a smooth plot which may be non-linear also.
Sir, I have a question. In case of correlation, do we always have two variables, or can we have correlation between more than two variables also?
Correlation between?
More than two variables.
Yes. You see, when well, I am because yeah, Anuradha had given me just 2 hours, so I did not had to get not had time to go for other things. But surely your question is valid. I am considering here only two variables, but yes, but surely there can be different situation. A group of variable and say group of variable, between them also we can find some sort of correlation. One variable with respect to a group of variable, we can find out the correlation coefficient, and that is called as multiple correlation coefficient, that you are going to understand when you try to study this multiple linear regression model. And then we also have partial correlation coefficient, means you are trying to study the effect of couple of variable after eliminating the effect of one or two variables at a time, right? So yes, so we have this concept, but yeah, but I am unable to cover them here.
No problem, sir. That was just a query because whatever the party sir was asking, if I have more than two variables, will the property that he asked will still hold valid, or it will change?
No. These are two different things. That thing will have different properties, and what I told you for the correlation coefficient, they will have different properties. These are two entirely different statistical measures. For example, I can give you a very simple example. Suppose if I say the outcome of the agriculture, does it depend only on one variable, I mean the yield versus quantity of fertilizer, or it depends on quantity of fertilizer,
No.
temperature, rainfall, humidity? So I would like to see that what is the correlation coefficient between the yield with respect to a group of variable, right? So this will have some different types of properties than this thing. Or I can say also, okay, I want to compute the correlation coefficient between yield and the group of variable after removing the effect of this rainfall. What will happen if there is no rainfall?
Okay, sir. Okay. Thank you so much, sir.
Right. Okay. So shall we proceed? Right. Okay. So now we are going to quickly review the rank correlation coefficient. And as I said, this rank correlation coefficient is a very simple thing. This is the same correlation coefficient that you have discussed, but now here the X and Y's, they are the ranks of the observation. What do you mean by here ranks? If I try to in a very simple way, that if there is a variable here X, and suppose I want to measure its height, 150 centimeter, 160 centimeter, 152 centimeter. So this is my observation, which has got the, say here, rank number 1. This is here rank number 2, and this is here rank number 3. Right? Or means that can be vice versa also, means how do you define the ranks, whether in increasing or say decreasing order. So these are actually the ranks. So means you can imagine that if there are two examiners, examiner 1 and examiner 2. Now a student comes, student number 1, and we ask some question, and suppose I give say 8 out of 10 and another gives say 7 out of 10. Then student 2 comes. Okay, we see the performance, and we try to give, suppose I try to give here 5 and this person gives here 6. So by looking at this data, can you see that we are going nearly the similar marks. But on the other hand, the more difficult part here will be that in case if I try to give here 8 marks and then this person tries to give here 2 marks, I give here, suppose here 3 marks, and this person gives here 9 marks. You will get confused that how these two judges are working, that they are trying to give such a different, that means there is no correlation between the findings of the two judges. So that is exactly we are trying to do here. And then we are not working on this here, this 8 and 3, but we will try to see if we have got this data, then this value is here rank 2, and this is here rank 1, for example, and so this is here rank 1 and this is here rank 2. So we will be finding the correlation coefficient between, say here 2 and here 1 and here 1 and 2, this type of xi, yi. So these are the ranks here. Right, so yeah, so that is what we expect, that I just shown you here. Right, so that we expect that we will give higher ranks to good candidates and lower ranks to the bad candidates. So anyway, so this rank correlation coefficient is going to measure the degree of agreement between the ranks of the two examiners, right? And for that we have this Spearman's rank correlation coefficient, or this is popularly called as rank correlation coefficient, but in the R software you have to give the option as a method as say here Spearman, so that it can compute and the correlation coefficient based on the ranks. Right, so let me try to give you here that how it is done, but anyway R is going to work for you. So if I say here rank of xi, this is the rank of the ith observation on x. That means you try to take the take all the observation, give them rank, and then the ith observation has got a rank. And similarly, we will have a data on the yi, that means the data on the judge number 2, and there also for the same student I try to find out the rank. So for every student there will be 2 ranks, one given by the judge 1 and say another by the judge 2. So and then we try to find out here the difference between the ranks. Well, that can be rank of xi minus rank of yi, or rank of yi minus rank of xi. That will not make any difference, because actually you can see here we are going to use here the square of this quantity. And then if you try to see here, this is the expression for the rank correlation coefficient. So this di is coming from here, and then n is the number of observation. So how it is coming, okay, that is our job. But anyway, the utility part is the same as that happened in the case of correlation coefficient. So in this case, this correlation coefficient is going to lie between -1 and +1, and the interpretation goes exactly in the same way as it earlier. If all the judges are giving the same rank to all the candidates, for example, I give 10 marks, other person gives 10 marks, I give 2 marks, other person gives 2 marks, then the rank is going to be +1. And if the opposite happened, that I give the highest rank and the other gives the lowest rank, then the correlation is going to be -1. And any value in between -1 and +1, that will indicate the magnitude and the direction of the correlation coefficient. So if the direction is -1, that means both the judges are trying to give their marks in an opposite way. And if the sign is positive, that means both the judges are working in the same way. Means good student, good marks, bad student, bad marks. But in the case of minus, good student, bad marks, bad student, good marks. And then magnitude is trying to say that, okay, what is the degree of association between the ranks of the two? Right. For example, if I say, okay, I give here rank 5, another gives here rank 6, I give here rank 4, another gives here say rank 3. So you can see that they are more or less close. Right. So now let me try to just give you a very simple example to show you that how the things happen, because many times I feel that student get or my participant get confused that whether means how are we trying to handle this DI versus XI YI. So if you say here with I am just taking here 5 students and judge 1 has given them this mark and then judge 2 has given them this mark. Now I simply try to see here these marks and try to give the ranks. So this is the lowest mark, I give it here rank 1. This is here the second highest mark, I will give here rank 2. Then we have here the marks 50, I give here rank 3. Then similarly I have here marks 75 rank 4 and 95 rank 5. Yes, you can do it opposite also, 5 4 3 2 1, but anyway you have to choose one. And the same process I have to follow here also in the second data. Right. So these are my rank of Xi and rank of Yi. I try to take the difference between their ranks, as I said here, that you can see here, this is here rank of Xi minus rank of Yi. So this is 4 minus 4, this is here 1 minus 5, this is minus 4, this is 2 minus 3 minus 1. So these are the values of my here Di. Now, once I use here summation Di square, this formula, I can get here the correlation coefficient is minus 0.7. So minus is, that means both judges are thinking opposite and their magnitude is 0.7. Right, and if you want to use it in the R software, this is very simple. You have to use the same command, COR. Use means since you are trying to use all the data, so by default it will be there even if you don't mention it here, but you have to be careful in writing that method is now equal to Spearman inside the double quotes and everything in the lowercase alphabets. Now, if you try to do the same thing here, right, you can get the correlation coefficient. For example, if I try to take here the same data set and I try to store it in the variable X and the same data set on Y, I try to store it in the Y here like this, and you can see here so basically your X is here judge 1 and Y is here judge 2. And if I try to find out here the correlation between judge 1 and judge 2 and I use here method equal to Spearman, I get here minus 0.7. Right, so you can see here this is here like this. So this is how you can find out the correlation coefficient between the two such ranked variables. Right. So and then if you try to do these things on the R console also, they are very simple things I will say here. Let me try to copy this data. Let me try to copy this data here and come to here R console. So you can see here. Means I just pasted the values, so you are getting here the same thing. Right. So now I will stop here in this lecture, and I would request to all that if you have any doubt, please ask. And our next topic is actually the test of hypothesis. So I would rather prefer that we can have a means break and we can meet after 15 minutes so that we can start completely afresh with this new topic. And if you try to see here, you just go to the same link where you went yesterday and you try to download the slide here. Right, so you can see here the things which I have shown you here. But anyway, yeah, if you have any questions, please ask.
If there are no questions, then we can have a break.
I think somebody has raised the hand.
Okay, doctor.
Yeah. Good morning, sir. Good
Good morning.
morning. Sir, we draw the regression line from x and y axis in between. How we calculate angle theta?
How do we
Calculate angle theta.
Yeah, I think
Angle
I think the speaker who is going to give you this means lecture on regression analysis, I expect that they will explain you. But anyway, I can give you the answer. And the formula will become here summation xi minus x bar yi minus y bar divided by summation xi minus x bar whole square. So, but in the R software, if you simply try to use the command here lm, that will give you the entire regression line.
Yeah. Actually, we will calculate that tan theta equals to
Pardon?
theta equals to that angle.
Yeah. Tan
We
theta is your
calculate
actually the slope
tan
parameter.
theta.
Yeah. Tan
Yeah.
theta actually, yeah. So means I have not covered that topic, so it is not appropriate for me to comment. But yeah, but whatever is the value of the regression coefficient, that will give you
Okay.
the value of the slope. And the command I can
Okay.
say here, this is very simple. If you have the dependent variable as y, or if you write y equal to a plus bx, then the command here is lm, and then within parenthesis you write y tilde x. That will give you the regression line, and then you can find out the value of the regression coefficient. That is going to be the value of the slope parameter.
Okay, sir. Okay. Thank you. Thank you, sir. Thank you.
Sir, in any mathematical book, you have the explanation.
Pardon?
Or in any mathematical or statistical book, you have the explanation to calculate the y is equal to a plus bx. So the value of b can be calculated as per that. I mean, the method is very simple. You can find out in the book.
Yeah,
Sir is trying to tell a solution.
Actually, there are different ways. Whether you want to use the principle of least square, then the method is different when you try to use the.
Sir, generally we use principle of least square generally, but if you are going for some specific analysis, then
yeah,
the method will be something different. But it is all.
I expect that anybody who will teach you the simple linear regression model, I expect that they will give you the complete details.
Yes.
So I wanted to ask that normally when the data is ordinal, that is the time that we use rank coefficients or we use the rank method. How
When
much
the data is
ordinal in nature, we should be using the rank coefficients. How much?
you have to convert the data into ordinal data.
Yes, sir. And
Data,
so normally
data will be data, but you have to now compute the ranks of the individual data and then try to find out the correlation between the ranks. And if miss on the other hand, if somebody gives you the data directly on the ranks, then you can find it out directly.
And sir, in case if the data is continuous, how much relevant is it to use the rank coefficients or methods which are based on rank?
Yeah, it is something like this. If I have got a body temperature, I go to a shoe shop and I ask him what is the medicine. These are two different things.
Okay, sir, because normally when we were finding Pearson's correlation, we used mean. So mean can only be used when the mean. And mean would only be used when the data is normal. Because that would be the proper measure of central tendency.
No. That's a 100% myth.
So we can use mean in terms where it is not normal also.
Yeah, means mean and normality. These are two independent concepts. Sample mean is sample mean. If you try to find out the distribution, if x1, x2, xn are coming from the normal distribution, then the distribution of the sample mean will also be normal. But it is, but sample mean can be computed from say any of the data. And if you try to go with the maximum likelihood estimation, there are many distribution whose parameter estimate comes out to be the sample mean.
Okay, so okay. Thank you, sir.
Okay, so we will break for this session.
Yeah, I
And at
think so.
what-
Otherwise, yeah, we have 15 minutes, and then yeah, starting a new topic will be difficult.
Yes, it is
Right. In the
difficult.
meantime, you can just download the slides from there. That should not be a big deal. I mean, that is the same link. Go to my homepage. There is a MIT University, and then you just download it.
Someone has put the slides on the group also. Someone has downloaded and put on the group also. So you can take from the WhatsApp group as well. So, sir, are we going to meet?
Pardon? I think I couldn't
Sir,
hear
at
you.
what time are we going to meet?
11:30.
Okay, sir. Okay. So we will meet at 11:30. Thank you so much everyone for joining this session.